All right, so let's get started with the big ideas in 4.3, and then tomorrow we'll just work through a couple of examples. And once again, most of the work you're doing this week, there's the conceptual work, right, which goes on up here, and then a lot of stuff you're working through is algebra and trig. So once again, if you need review for that, let me know. All right, so 4.3, what derivatives tell us comes back to, well, the first part comes back to this. Differentiability means locally linear. So geometrically, the derivative is the slope of the tangent line. Geometrically, the tangent line is the line you get when you zoom in on a graph and you see a line. Okay. So what's the first derivative tell us about graphs? If f prime of x is always greater than 0, then think about it. What that means is, as you zoom in locally, the slope is always positive. You follow? So if the slope is always positive at every point on the curve, then the entire function, the entire curve, is increasing over that interval. So increasing at every point means increasing over the whole thing. So this is kind of a reverse of what we had been doing. When we got the derivative, we looked globally between points and shrunk it down to one point. You follow? Now this is taking information at individual points and then blowing it back up to talk about what's happening on the interval. So that's kind of the idea. When we defined the derivative, we took the limit to take global, whoops, if I could spell, back to local. Right? The mean value theorem is going to help us take local behavior back to global behavior. Okay. So so let's just assume f prime of x is bigger than 0 for all x in an interval containing a and b, where a is less than b. To show that the function itself is increasing, I need to show that f of a is bigger than f of b. So I want to show that f of a rather, is less than f of b. So here's a and here's b. I know that the derivative for all points is positive. I want to show that this means that the graph has to be increasing the whole time. You follow or not, folks? That's what it means. Well, here's the proof. I look at the mean value theorem. The mean value theorem says there's some point C between A and B where f prime of C equals f of B minus f of A over B minus A. But I also know that at all points the derivative is what kind of number? Positive. So I know this is a positive number. I know that f prime of C has got to be bigger than 0, which means f prime of C has to be positive. So I know that this has to work out to be a positive number. You follow? Well, b minus a itself is what kind of number? If a is less than b, b minus a is what? That's got to be a positive. So the only way I've got a number over a number being a positive number is if the number up top also has to be what? Positive. Make sense or not? Which means that f of b has got to be bigger than f of a. Boom. So the mean value theorem, once again, the mean value theorem is a statement about global behavior being mimicked locally, and then when you put enough of those together, that gives local behavior helping us understand global behavior. So it's kind of a reversal. Right? And these are big highbrow ideas you might need to think about. Similarly, if the derivative is negative, then that means that the function is going to be decreasing. Make sense? And if the derivative is 0 all the time, then what has to be true all the time? Function has to be constant. Make sense? This actually will come back to help us out quite a bit. What, next week? I think it's next week already. In other words, if the derivative is always 0, and once again, this is a positive number. The only way to get a 0 out is if the numerator is what? 0, which means f of a and f of b have to be what? Make sense? So there it is. That's what the first derivative tells us. What's the second derivative do? Well, let's take a look at these things here. You notice that there's kind of two different ways you can be increasing. You can be increasing like this or increasing like this. You follow? You see how they're different kind of phenomena? If you look at the slopes here, these slopes are getting steeper. You follow? And since they're all positive, that means that they're getting bigger. You follow? So we have increasing slopes here. Meaning that they're more positive. Over on this side, we have what kind of slopes? These are decreasing slopes because they're becoming less positive. Does that make sense or not? So if we're looking at the slopes themselves increasing or decreasing, then we need to look at the derivative of the slope function, right? And what function gives us slopes? The first derivative. So I need to take the derivative of that. Does that make sense or not? So the second derivative is going to tell us about what's called concavity. All right? So concavity comes in two different flavors. You've got this is what they call concave up. This is what they call concave down. So let's look at what the slopes are doing in a concave up situation versus a concave down situation. There you go. So if you look at what the slopes are doing here, they're steep, but what? Negative. And as we go down here, they get less steep, they're getting less negative, and then at the bottom they zero out, and then they start becoming what? Positive, and then more positive, right? So they're becoming less negative and more positive, which means that those slopes are increasing. You follow? They're getting bigger each time. Less negative means they're increasing. So this is where the second derivative is positive. Second derivative is positive means the slopes are increasing. So they're either becoming less negative or more positive depending on the situation. So there you go. The positive happy face, you may have seen this for quadratics. There's a good reason for that. We'll talk about it in Calc 2. All right, now let's look at concave down situation. If I imagine these little pieces of tangent line coming in here. Here the tangent lines are pretty steep, but they're steep and positive. They become less steep, but still positive. Then they zero out. Then they turn negative, and they become more and more steep, but they become more and more what? Negative. So in this case, all the slopes are decreasing. They're either becoming less positive or more negative. So here, the second derivative is negative. The slopes are decreasing. So they're either becoming less positive or more negative. And so that's your concave down. That's the sad face. All right. So if you look within each of these parabolas, you've got increasing and decreasing. So if I look at, for example, the concave up scenario, right? So there's your concave up. Think there's happy face. You got on the left side here, you've got the derivative is negative, and on the right side you've got the derivative is positive. So you can be concave up but decreasing, or concave up and increasing. Make sense? On the second derivative is negative, you get that. Once again, if you look, you've got two different sides. Here you've got the first derivative is positive, or the first derivative is negative. And so when you combine the first and second derivatives, that's going to tell you what a pretty good idea of what the graph is looking like. So for example here, f prime is positive. That just tells you that the function is increasing. So pretty much you have, this is what's happening if f prime is positive. But if I refine it and tell you that f double prime is also positive, that tells you it's positive but concave up, and that gives you that bend. You follow? Here, the second derivative is negative, so that's a concave down. So that's how the second derivative helps refine what's going on. We know that f being differentiable means that f is locally linear. And so we talked about how we could use the mean value theorem to prove the following. So if you have f prime of x bigger than 0 or positive on an interval I, then f of x is increasing. All right? So remember, the derivative is the what on the graph? Derivative is the slope. So if the slope everywhere is positive, then that means the graph of the function overall is increasing. So that's taking what's happening locally at every point and then extrapolating it, bless you, to globally over an interval. If f prime of x is less than 0 or negative on some interval I, then that means that the f of x is going to be what? Decreasing. Negative slopes everywhere means that the global behavior is the function's trending downwards. And if f prime of x is equal to 0 on the interval I, then the f of x is what? The derivative is 0, that means what? It's, constant. So it's a horizontal line. So this is what we talked about here. And so we're taking the idea of locally linear and then bringing it back to this global behavior. All right? Now the new thing we talked about yesterday is what the second derivative tells us. So if f double prime of x is bigger than 0 or positive, then that means the graph of f of x is what's called concave, I can spell, up. And so, that's the old thing. And as you'll see in Calc 2, just like the first derivative tells you about local linearity, the second derivative tells you about local quadratic behavior. So the reason why this gives us sort of the curvature like a parabola is because there's actually like a tangent parabola in there. Okay, and depending on how things shake out, you might see a problem like that towards the end of the course. Normally in Calc 1 and 2, the last assignment is a project. But with an 8-week course, there's literally, I don't think, just the time to try to get a project squeezed in. So you'll have some other sort of comprehensive assignment for your last assignment. But it'll be just like everything else. You know, every week there's a 50-point test, a 50-point take-home. So I'm thinking on that, the take-home, I might give you a little preview teaser of Calc 2, looking at these local parabolas. If the second derivative is negative, then that means locally it looks like a sad parabola. And so you can see within each of these increasing and decreasing. So if you have the first derivative positive and the second derivative positive, then that means you're increasing in concave up, so you're on this half of the parabola. If the first derivative is positive but the second derivative is negative, then you're increasing in concave down, so you're on this half of this parabola. If the first derivative is negative but the second derivative is positive, then that means you're decreasing but concave up, so you're on this half of the parabola. And if you're decreasing and concave down, then that means you're on this half of the parabola. Make sense or not, folks? All right, so that's sort of so what we're going to do now is we're going to go through two exhaustive examples that are algebraic, that take us through a function. We take its first derivative, analyze that, find out where it's positive, negative, 0. We'll look at the second derivative, analyze that, find out where it's positive, negative, and 0. And then using that information, we'll be able to cobble together a fairly decent representation of its graph. All right. And then there's a couple videos for you to watch where we go through the same thing with the trigonometry. All right, so once again, the example videos, I expect you to either work through those examples or watch the videos. When people come into calculus, the one thing they're probably rustiest on is the trigonometry. So a lot of times what I found over the years is when I go through an example on trig in class, if you can't pause things and remind yourself of the identity, it just looks like a magic show. So the nice thing about a video is you pause it, you go, oh wait, that's an identity, let me go look it up, let me think about it, whatever. So that's the idea anyway. So let's take a look at this polynomial here. So we're going to take this, and so in the handout we do first derivative stuff, then we talk about second derivative and second derivative stuff. So we're going to be working through example 1, and then example 1 and 4 work with the same function. Oops. So example 1 and 4 are both working with our this cubic polynomial, x cubed minus 3x squared minus 9x plus 5. Okay. Example 1 talks about looking at the first derivative. What's that tell us? Example 4 tells us, or has us look at the second derivative. We'll just do it all together. Okay. So let's take a look at the derivative. So first things first, what's the derivative here of x cubed minus 3x squared minus 9x plus 5? So what do you get for the derivative there?
3x squared minus 6x minus.
Perfect. Okay. And now what we want to do is we want to make a sign diagram for f prime. So to make a sign diagram, we need to look for any places f prime of x does not exist, and then we need to look for where f prime of x equal to 0, and then we need to test f prime of x between the critical numbers. So between these things. Okay? So looking for the derivative does not exist. What are we looking for? Are there any divisions by 0 that could possibly happen here? Are there any square roots we have to worry about? So we're totally fine. So there are none of these, so we've checked those off. Now we just got to set the derivative equal to 0. This is a quadratic equation. Once again, there's a review on factoring in quadratics if you need it. The first thing we could do, though, to get started is what? What's a common factor among all those terms? I can get a 3 out of it, and I'd be left with an x squared minus a 2x minus a 3. And now we look to see if this is easily unfoilable. If I'm going to unfoil it, I got to split the x squared to x and x. Can I get factors of negative 3 that add up to negative 2? So what are they? There you go. Now I've got 3 factors, 3 real numbers that have multiplied together to give me 0. The only way that happens is if one or more of them are 0. Can 3 ever be 0? So either x minus 3 is 0 or x plus 1 is 0, or both. From x minus 3 equals 0, we get x equals 3, and from x plus 1 is 0, we get x equals negative 1. So this is where the derivative is 0. So now what we do to make a sign diagram for the derivative is we're going to put the places, we're going to put the critical numbers up there, and then we're going to test in between it. So here's the sign diagram. So I like to put the number line there. Below I'm going to have the f of x's. Above I'm going to have the sign of the derivative. And then above that I'm going to put the behavior of f of x. This is typically how I do this. There were no places where the derivative is undefined, so I just looked for where the derivative is 0. That's at negative 1 and 3. So I'll put a negative 1 there and a 3 there. And the derivative is 0 there, so I'm going to put a 0 above them. And since the derivative is continuous on those intervals, I can go ahead and take any value I want. I can take a test value, and the sign, the SIGN, the plus or minus, will be the same regardless of which number I pick less than negative 1. It'll be the same regardless of what number I pick between negative 1 and 3. And it'll be the same regardless of what I pick bigger than 3 because of the intermediate value theorem. So it doesn't matter what number you pick. Give me your favorite number less than negative 1. Negative 2. What's your favorite number between negative 1 and 3? And favorite number bigger than 3? Right. Doesn't matter which number you're going to pick. What we do is we plug that into the derivative. And, you know, once again, you have Desmos at your disposal, so you could always just, I guess, plug it into there. Or you could take advantage of the factoring you did. Because all we're interested in is the sign, the SIGN sign, plus or minus. So if I plug in like a negative 2, I've got a positive 3. Is this factor going to be positive or negative? And then this... I'm sorry, it's x plus 1. So this will be a positive, this will be a negative, this will also be a what? So when you multiply that out, that's going to be what kind of number? That's going to be a positive. And once again, you could pick negative a billion to plug in. there's no way the derivative is going to change from plus to minus, because to do that, it either has to jump across at a DNE or it has to cross through at a 0. And we found all those places. You follow? So that's your intermediate value theorem working. When you plug in a 0, you get a positive 3 times a what? Negative times a positive. So that means this whole thing's going to be negative. And when you plug in a 4, you've got a positive 3. That's going to be a positive, and this is going to be a positive, so that's going to be a positive. And now let's interpret what that means in terms of the graph of f. The derivative is positive. The derivative are the slopes of, that's the local linearity. So positive slopes mean what? Increasing. A 0 slope means what? A negative slope means, a 0 slope means, a positive slope means. So you see how we're getting that interpretation. All right? That's what the first derivative is telling us. Now, just looking at this information, we can already identify local extrema. For example, at -1, it's increasing, it flattens out, and then it's what? Decreasing. So what kind of features do we have at the graph there? Be a local maximum. Does that make sense? And then it's decreasing, flattens out, and increasing. So that would be a local what? Minimum. And that's what they call the first derivative test for local extrema. So this is an example of that. If f prime changes from positive to negative, then you've got a local max. If it changes from negative to positive, then you got a local min. If it doesn't change at all, then that means the function flattens out or does something or gets goofy. We'll see that in the next example, and then just continues on its way. All right, so there is no local max or min. Okay, let's move into the second derivative. So let me record our first derivative again. Now let's move on to the second derivative. And what is the second derivative there? Six x minus 6. And once again, we're going to make a sign diagram for this. So we need to know where the second derivative does not exist. Then we look for where the second derivative is equal to 0. And then we make our sign diagram by using test values. So once again, are there any places where this second derivative is not going to exist? That's a lot of negatives in there, but any chance we can divide by 0? Any issues with radicals or anything? No, we're all good. So I just set the second derivative equal to 0, and I think we have space here to do that. If 6x minus 6 is 0, what do you get for x? X is what? 1. All right, so now we're all ready to get our sign diagrams. So once again, here's my x values. Here's my f double prime of x. And then I'm going to see what that means about my function f of x. The only critical value we got was x equals 1. And at x equals 1, the second derivative is 0. And now I'm going to plug in some test values. So what's your favorite number to plug in less than 1? 0. Favorite number to plug in bigger than 1? 2. Once again, you pick your own numbers. We're plugging them into 6x minus 6. If you substitute 0 into 6x minus 6, what do you get? Positive or negative? Negative. You plug in 2 into 6x minus 6, what do you get? Positive. And once again, your test values don't matter. You'll still have the same plus or minus on the interval, thanks to the intermediate value theorem. Now we go back, we're looking at the second derivative. So first derivative, think of first degree polynomials, linear, local linear, slope. second derivative, think second degree polynomials, think quadratics, think parabolas. If you have a parabola with a leading coefficient that's negative, is it concave up or concave down? Concave down. If the second derivative is positive, it means it's concave up. Okay? All right. So f is increasing, decreasing, concave up, concave down. So let's go back and record all this information. When we talk about where is the function increasing, where is it decreasing, etc., we're looking for the x values. So where is it increasing? So it's increasing here, and that's for x's that are less than -1. So we can think of a minus infinity here and an infinity here. So minus infinity up to -1. Comma. Where else is it increasing? 3 to infinity. Perfect. Decreasing. Once again, we go back to the first derivative. Where is it decreasing? Between what? -1 and 3. Concave up. It's concave up on what interval? Once again, feel free to put in the infinities there to help you. It's concave up from where to where? 1 to infinity. And it's concave down from where to where? -infinity to 1. Okay. Now, from the increasing and decreasing bit, we picked up some local extrema, right? We went from increasing to decreasing and decreasing to increasing. So let's record those. So local extrema. We had a local max at -1, x equals -1. So at -1 comma f of -1. So we'll figure out what that is here. Get the original f of x. Okay. All right, so if I plug -1 into that, I'm going to get a -1 out of there. A -1 squared, which will be a what? +1. So -1 minus 3 is a -4. And then a -1 in there is going to make that a what? +9. So -4 plus 9 is... 5 plus 5 is 10, so -1, 10. And then we also had a local min at 3, comma f of 3. So you plug in the 3 there. 3 cubed gives you 27. 3 squared gives you 9, times 3 gives you 27. So these things are going to do what? Cancel out. This gives you another what? 27, but it's negative. Plus 5 is -22. And so, you might well wonder, well, we've got a special name. When the first derivative changes, that creates what's called a local max or local min. Is there a special name for what happens when the concavity changes? And yeah, there is. That's called the inflection point. Out in the wild, it's sometimes called a point of diminishing returns. We'll talk more about that when we get into the exponential functions at the end of the course, which will be in like 3 weeks. But yeah, so we have an inflection point. So inflection point an inflection point, this is a point on the graph where concavity changes. And sure enough, the concavity changes when x is equal to what? 1. So 1 comma f of 1. So you've got 1 minus 3 minus 9 plus 5. So what's that all add up to? Minus 6. Okay. So let's put all this together and sketch a graph. And then we'll fire up Desmos and see how good we got. Because the thing about, we've had this mantra in this course that technology can suggest and confirm solutions, but it's the mathematics that proves it. So oftentimes the mathematics will reveal behavior that the graphing utility, unless you do things just right, will hide from you. So let's see here. We got, so I go through here, we've got negative 110, that's a point on the curve, so that's something to pay attention to, so we'll call that 10. So negative 110. We got 3 comma negative 22. And we got 1 negative 6. Okay. So let's see what's going on here with this function. So let's see, I've got coming up to negative 1, coming up to 1, and coming up to 3. So looking in this interval, when x is less than negative 1, the function is increasing and concave down. You follow? So increasing and concave down, put that together, means it's got to look something like that. Make sense or not, folks? Now I know that at negative 1, the derivative is 0, so it flattens out, creating that local maximum. Okay? And now I look to see what's going on between negative 1 and 1. Between negative 1 and 1, it switches from increasing to what? Decreasing, but it's still concave down. So decreasing and concave down means it's going to look like that. So it's got to come up, it's going to level out, and then it's going to come down. So you see how it's concave down this whole time? It just went from increasing to decreasing. Now what changes at 1? From 1 to 3, it's still decreasing, but now it changes from concave down to concave what? Up. So now from here, between 1 and 3, it's concave up and decreasing. So it looks like that. Until it gets down to 3. At 3, the derivative is 0, so it flattens out. It's still concave up, but it switches from decreasing to what? Increasing. That little knob there is very sensitive. So there you go. There you go. And what we could do is we could check, if I looked at the limits as x goes to minus infinity, which is what we did, and this is where the next section comes into play. So in the next section, 4.4, we just go back and revisit end behavior and all the asymptote stuff. All right. Because if I can look at those limits and I know how things are going, then I've got a pretty good graph. So do you see how we piece together the information interval to interval? That's kind of like how I like to do it. I do a first derivative analysis, second derivative analysis. You plug in to find all the key points on the graph where things are changing, and then you just kind of piece it together. Make sense or not? If I wanted a more detailed graph, I could go in and I could do some algebra, because according to our picture here, how many x-intercepts am I going to have? 3. So we could go and do some algebra on that to tie those up. So let's see how we did with Desmos. Let's plug in our numbers. -1 was a point to have. 1 was a point that was important, and we had something at 3. Okay, and there it is. So I guess if we wanted to be a little, let's go maybe -5 to 5. We don't need that much that way, and then for the y, maybe -25 to 25. Should be able to capture all our stuff that we got. There it is. Okay. So do you see on the graph here, the max and the min we've looked at before, but the new thing is this inflection point. So it's concave down, so it looks like an unhappy parabola, but then at 1, -6, it switches to being a happy parabola. Okay. And we haven't studied these kinds of functions yet, but we will at the end of the course. These are also sometimes also called the point of diminishing returns. There's a class of functions called logistic functions which model all kinds of things, but one thing they model is sort of like advertising dollars and then getting to the public. So let's say you're advertising. The more money you spend on advertising, like the more commercials you run or whatever, ostensibly the more people you're going to reach. You follow? But at some point you're not getting as much reach as you did before. So even though you're getting more, right, more people to see your ad, the rate at which you're gaining that exposure is decreasing. So that's called a point of diminishing returns. So, for example, here you can see that's what the inflection point is. It's the point where your first derivative has a local max. In other words, here you go, you've maxed out. So this is the steepest this curve gets. You follow? After this, it becomes less steep. It's still positive, but less steep. So if you ever heard of that point of diminishing returns, that's a point of inflection. It has to do with concavity. All right, any questions on this first example? You see the strategy here? So once again, the calculus concepts, most people glom onto those pretty quickly. It makes sense. It's the nitty-gritty of the algebra and the trig. So let's do a more involved algebraic example. Looking here, example 2 is the first derivative analysis for this function. So this is example 2 and example 5. So we got an x to the 4/3 minus 4x to the 1/3. And just to kind of remind ourselves here what these powers are doing, remember the denominator in the exponent is the what? Is that the power or the root? That's the root. So this is like the cube root of x to the fourth, or just the cube root of x. You with me or not? Okay. Now, I usually don't turn them back into radicals unless I'm solving equations with them, because normally when you do calculus, you just want to keep them as the fractional exponents, because then you can do power rule on them. So let's take the derivative here. What's the derivative of x to the 4/3? So it'd be 4/3 x to the 1/3 minus, what's going to, bless you, what do you get here? You get a 4/3 x to the negative 2/3. And in order for us to more easily figure out where the derivative doesn't exist and where the derivative is 0, we want to get common denominators and things like that. So what do you remember about these negative exponents? When you have a negative exponent, it really means that this factor of x to the 2/3 resides where? It's really, yeah, this is in the denominator. So let's write this here. I've got a 4x to the 1/3 divided by 3 minus a 4 divided by x to the 2/3. So x to the 2/3 is down in the denominator with the 3. So when we go to get a common denominator to help us with our calculations, I need to have a factor of 3, but I also need a factor of what? X to the 2/3. So this is going to be 3x to the 2/3. Looking at this first fraction, I have the factor of 3. I'm missing the factor of what? X to the 2/3. So I'm going to multiply by x to the 2/3 on that term. Am I missing anything from the common denominator here? No. So this is minus 4. So that's 4x minus 4 over 3x to the 2/3. So this is going to be easier for us to work with. You follow? So let's take a look at that. Because from this I can easily tell where the derivative doesn't exist. F prime isn't going to exist when what happens? Yeah. So it won't exist when the denominator is 0, which is going to happen exactly when x itself is what? 0. We all cool with that? And I can also readily tell when the derivative is 0, because since I have a fraction, the derivative is undefined when the denominator is 0. The derivative is 0 when the what? Numerator is 0. And that happens when x is what? 1. Okay? So I'm all set to make my sign diagram. Whoops. Give myself some room here. We'll use this part for the testing part. So we got a minus infinity to infinity. We got a 0 and a 1. These are my x values. Then I'm going to have my f prime of x values. Then I'm going to see what's going on with f of x. Now, this is something new. When x is 0, the derivative is undefined. So I'm going to put a question mark there, because that means there's something going on there we don't quite know. The derivative is 0 when x is equal to 1, and now we can just test our values. What's your favorite number to plug in less than 0? Negative 1. What's your favorite number to plug in between 0 and 1? A half. Favorite number bigger than 1? 2. Now once again, we're not concerned with the actual retail value of what happens when you plug it in. We just need to know if it's positive or negative. So let's look at f prime of negative 1. The numerator is going to give you what kind of number? What about the denominator? What's going on here? I got a 2/3 power. The 3 means it's the what root? Cube root. The 2 means it's what power? Squared. So if I take a negative, and I take the cube root of a negative, it's going to be a negative, but then I'm going to turn around and do what? Square it. So this would be a positive, which means the entire fraction would be a negative. We all cool on the analysis here? Now I plug in the half. In the numerator, I plug a half in. What kind of number do I get? Negative. In the denominator, I've got a positive to a power times a positive, so that's going to be a... So that is still a negative. And now I plug a 2 in. Positive, positive, so what? Positive. So I'm decreasing, something happens, I'm still what? Decreasing, and then what happens? I level out, and then I start to increase. Make sense or not, folks? All right. So now it's time to move on to the second derivative. So we need to start with the first derivative. So this version of the first derivative was very good to help us with the algebra piece of this. You follow? But it's not so good to help us with the calculus piece. This version of the derivative is more friendly to help us take the derivative of. You follow? So we'll go back to that. So we'll look at 4/3 x to the third minus 4/3 x to the 2/3. Negative 2/3. Thank you. All right. So you see the difference? We'll pick the form that works. So take the derivative of this. I'm going to get the third comes down. The 4/3 is going to turn into a 4 what? 9ths x to the minus 2/3. And what's going to happen here? That's a positive 8/9 x to the minus 5/3. Now in this case, both of those x's are going to wind up where? The denominator. So this is going to be a 4 over 9 x to the 2/3 plus an 8 over 9 x to the 5/3. And now I need to get my common denominator. I need a factor of 9 for both of these. And then what factor of x do I put down there? Remember, when you get common denominators, you're looking for the least common multiple, right? So when you're doing least common multiple, that means that you're always going to pick the higher power of x. So now looking at my first term here, I've got a 4. I've got the 9 already, so that's fine. I'm going from an x to the 2/3 to an x to the 5/3. So I'm missing how many x's? How many factors of x am I missing there? 3/3, aka x to the what? First. Right. So x to the 5/3 is x to the 2/3 times x to the 3/3, which is x to the first. So that's just an x there plus an 8. And once again, we've changed the form of the second derivative to make it something that we can more easily work with for sign diagrams. So let's go. I'm going to recopy this to the next page so we have room. Any questions on getting that second derivative? All right, so we look where the second derivative does not exist. Once again, we have an x in the denominator. So if you set 9x to the 5/3 equal to 0, what's the only value of x you get from there? Now we look for where the second derivative equals 0. That's where we set the what equal to 0? Numerator. So what do you get for the x there? -2. And now we're ready to go with the sign diagram. So we're going minus infinity to infinity. We got our x equals 0, and we got our x equals -2. I guess I should put that over here. And we're going to look at the sign of the second derivative and then figure out what that means for the first derivative. So once again, the second derivative doesn't exist at 0, so I got a question mark there. And hopefully that's no big surprise, because the first derivative didn't exist. So if the first derivative isn't continuous, then the second derivative can't be continuous there. You follow? So hopefully that makes sense. In other words, once you lose an x value from a derivative, it's never coming back. It's gone for good. All right. -2, second derivative was 0, and now we test. Whatever you want to test. Now when it comes to this denominator, 5/3, once again, the 3 represents the root, and the 5 is the power. So these are both odd powers. So negative numbers to odd powers are going to stay what? Negative. Positive numbers to odd powers are going to stay positive. So you plug a -3 in there. The numerator would be a negative. The denominator would be a negative. So it would all be a positive. You plug in a -1. The numerator is a positive. The denominator is still negative. You plug in a 2. Numerator and denominator are now both what? Positive. Any questions on getting the signs of the second derivative? All right, we're looking at the second derivative now. Second derivative, think second degree polynomial, think parabolas. You've got a parabola, leading coefficient positive. Is that a happy or sad parabola? And then here it's okay. So now let's write down all the information we've gathered from these and try to piece together the graph. So we've got increasing, decreasing, concave up, concave down. Any local max, any local min. I'll give myself some room here. Any inflection points. Okay. So increasing and decreasing, local max and local min, we go back to the first derivative for that, local linearity. So it's decreasing up to 0 and then decreasing from 0 to 1. Now, is the function defined itself at 0? The derivative's not. But is the function itself okay at 0? Any negative exponents here? No, so we're totally fine. So it's decreasing through 0. Okay? So it's decreasing from minus infinity up to 1. Does everyone see why we can just go right through 0 there? Okay. Now, if 0 weren't the domain, then you'd have to break it up into two different parts. Does that make sense or not? But as it is, and we'll see this when we check it. Then it's increasing from 1 on out. So as far as local extrema is concerned, using the first derivative test for local extrema, it's decreasing to 1, and then it flattens out, and then it starts to what? Increase. So that means at 1, we've got what kind of feature? Local min. So local max, there's none. Local min at 1 comma f of 1. And so let's see what that's going to be. Let's put the f of x up here. X to the 4/3 minus 4x to the 1/3. So if I plug 1 into this, I get 1 to the 4/3 minus 4 times 1 to the 1/3. That's going to give me what? -3. So I've got a local min at 1, -3. Let's look at concavity. It's concave up where to where? Minus infinity to minus 2. And then it's again from 0 to infinity, concave down in between. Okay. Inflection points. Inflection points are points on the graph where the concavity changes. The concavity changes at what two numbers here? -2 and 0. All right, so if I plug -2 in, I get -2 to the 4/3 power minus 4 times -2 to the 1/3 power. So we're going to go on to the next slide and simplify that. Let's plug the 0 in though. I got 0 to the 4/3 minus 4 times 0 to the 1/3. 0 to any positive power is what? 0. So that's one of the inflection points, 0, 0. So let's talk about the f of -2 to some little algebra review here. Okay, properties of exponents. You've got 4/3 power. 4/3 is 1 1⁻. You follow? So I've got an entire factor of -2 times -2 to the 1/3. So here I've got, once again, -2 to the 1/3 is the cube root of -2. And what can I do with the negative under a cube root? Move it out. So I'm going to have a -2 times a negative cube root of 2 minus 4 times a negative cube root of 2. So here I'm going to have how many cube roots of 2? So when I simplify, I get how many altogether? 6 of them. And so that's my other inflection point. I've got -2, 6 cube root of 2, and 0, 0. So I get 2 inflection points. Okay. Any questions on the algebra there? And there's another one on the another video where we go through that cube root. There's a cube root function on there. Was on a video from Monday as well. You go through with that parameter A. So let's put it all together and try to graph it. So once again, what I like to do is try to put everything together. So at 0, we've got a couple things going on. At 0, 0, we have an inflection point, but we also have something happening with the derivative. The derivative doesn't exist there. So something extra spicy is happening at 0, 0. We got a local min at 1, -3. We got something going on at 2, negative 2 comma 6 cube root of 2. So negative 2, 6 cube root of 2, it's going to be like, I don't know, 7 and 8, something like that. Something up there. We'll just call it that. Okay? So negative 2, 0, and 1. So let's see what's going on. Up to negative 2. Up to negative 2, we are decreasing and concave up. So decreasing but concave up. I'm gonna move this down a little bit so we can see it. So decreasing and concave up. So it's looking something like that. You follow? And then at negative, between negative 2 and 0, it's still decreasing, but it switches to concave what? Down. So then here it switches to concave down. Now coming into 0, what's going to happen? The first derivative at 0 is undefined, but on the other side of 0, it's decreasing but concave what? Up. So what kind of feature must be happening there? It's decreasing and concave down, the derivative doesn't exist, and then it's decreasing and concave up. So what kind of feature is that going to be? That's one of those vertical tangents. Make sense or not? That's how we can detect those second derivatives. So it's going to come in and go straight through here. So we got a vertical tangent. So it comes in, straight through, comes out. Now at 1, the derivative is 0, so it flattens out. And then, on the other side, it turns to increasing, but it's still concave what? Up. And there it is. And once again, we could take the limits as you go off to plus and minus infinity, like we did before, and get that they're both infinity, and that tells us that keeps going up forever now. Okay. Any questions on how we piece it together? Let's fire up Desmos. This is x to the 4/3 minus 4x to the 1/3. We had 2 comma f of negative 2. We had 0 f of 0. We had 1 comma f of 1. And let's check here, what's 6 times the cube root of 2? Check our decimals here. So notice we had 6 cube root of 2. That's roughly 7.559. Desmos is reading that as, so that checks. And that checks everything else. Now the thing is, if you look, it's kind of hard to tell, but there is an inflection point here. So this is something that Desmos might not be obvious. You can certainly see the vertical tangent there. Follow? And see it changes from concave down to concave up. But this inflection point is easy to miss. Now if you zoom out enough, you can kind of see how it becomes concave up. You follow? But that would be something that the math would pick up that Desmos, depending on your viewing window, may not. Okay, there's a video that does first and second derivative on the trig stuff. And then there's a video that goes back and revisits this function. This has a parameter in it that does that one. Okay. What else do I want to mention here? Oh, the second derivative test for local extrema. So the first derivative, you can see clearly if it's increasing and then decreasing, it's going to be a local max, decreasing, then increasing, local min. Second derivative test for local extrema. And if you need to take multivariable calculus at some point in your future, you're going to see a more generalized version of this. It says if f prime of c equals 0 and f double prime of c exists, then if f double prime of c is positive, well, think about it. F prime of c is 0 means that it's locally flat. F double prime of c is positive means it's concave what? Up. So if I put these two things together, that gives me a local min. If f double prime of c is negative, locally flat, but now it's concave down, that gives me a local max. And if f double prime of c equals 0, then who knows? It just means it's extra flat there. So it could be extra flat and have a minimum, it could be extra flat and have a maximum, or it could be just extra flat and have neither a maximum nor a minimum. You follow? So at that point, there's nothing you can say about it. All right, let's finish up here looking at example 8. Example 8 gives you the derivative of a function. It says assume as x goes to plus or minus infinity, f prime goes to minus infinity. So in other words, you can assume that there's arrows that go like that on it. So let's check it out. So this is the graph of the derivative. So the derivative is 0 at what points? You follow? Now, over here, the derivative is below the x-axis, which means the derivative is what sign? Positive or negative? Negative. Between 0 and 4, the derivative is above the x-axis, which means it's positive. And then over here, it's what? Negative. So what's going on with my graph of the original? If the derivative is negative, the original function is what? Decreasing. And then it flattens out, and then it increases, then it flattens out, then it decreases. Okay. So what's going on at x equals 0? We have a local what? Min. What's going on at x equals 4? A local max. Okay. Use the graph of f prime to make a sign diagram for f double prime. So remember, f double prime is the derivative of f prime. Okay. So if I look at where f prime is increasing, that's where the second derivative is positive. So if I look back at my graph, once again, this is the graph of the derivative. The derivative is increasing up to what? 2, and then it's what? Decreasing from 2 on. You see how we're getting that from the graph? Now, if the second derivative is positive, that means the original is concave up and then concave down. And so we can put all that together. It's concave up, decreasing, then increasing, and then increasing, and then decreasing. This place is concave down. And we don't know what's happening out here or out here because we don't have the original function. You follow? But you see, if you get the derivative, then you have enough information to sketch the shape of the graph. The original function is essentially determined by the derivative. We're not quite sure about the end behavior, and we're not quite sure about the vertical placement, but we can still get the general shape. Okay, and so that's the gist of it. That's what derivatives tell us. They tell us about increasing, decreasing, and the concavity. And plenty of practice there.